Hey YouTubers, Electric Adventures here with the next episode in Let's Make a Retro Game. I know it's been a while between episodes, but these actually take me quite a long time to produce, and I like to be well prepared and everything like that. The notes for this episode have been ready for quite some time. But anyway, it's here now, so let's get on with it. So this is the second half of my mini Z80 tutorial. So this is what I think you at the very least need to know to understand the code we'll be looking at in the next set of videos. So there's a fair bit in this video, not too many slides, but there's a lot of words on these slides that will come up in this video. So we'll see how we go. We'll work through a bit, and I'll try to explain it as best as I can. So obviously in this episode we're mainly going to be concentrating on things called flags that tell you what's happening inside the Z80 processor at any point of time. And they're very useful because they allow you to make decisions and things like that. So, and that thus leads it to jumps, which allows you to jump around your program. And then I have a little section on bits, bytes, and nibbles. Now, once again, I suggest you get a copy of, either electronically or physically, Programming the Z80 by Rodney Zacks. It is one of the best books out there for learning Z80 programming. So I referenced that in my last video as well. Okay, so on to our first semi-topic in here, which is loops and conditions. So any programming language needs a way that different code can be executed. So it doesn't just run one statement after another. Normally you want it to jump around and do loops. And I'm showing that here with you execute a task, you make a decision, and then you can go back and do that task again. What if you wanted to do the same thing a few times? So repeating tasks, decisions, and also code reuse. Sometimes you can actually make code faster by what they call unrolling it and just repeating the same set of code. But that often makes code very hard to understand, so it's only really for advanced tasks when you need the speed performance. I won't be covering any of that in this series. In this series I'm going to try and make code as readable as possible so all you guys can follow along and get started. So next we need to look at Z80 flags. So the very first flag is called the signed flag, and it determines whether the accumulator, remember from the last episode, the accumulator is one of our registers or internal memory locations inside the Z80 processor, and it's the main register that does all the maths inside the computer. So the sign flag determines whether a number or a result is negative or positive. So 0 means positive and negative is 1, and that is stored in bit 7, or the very last bit on the left of a byte. Now we will get into bits and bytes a bit more later. So next we have the 0 flag. That one's really simple. That basically tells us whether or not the accumulator is 0 or not. So if it's 0, it's set, and if it has any other number in it, it will be not set. Now the half carry flag is an interesting one. If you think about a byte of memory, it has 8 bits. Well, if you divide that in 2, you've got 4 bits in the lower half and 4 bits in the upper half, and they're called nibbles, and more on those later. The half carry flag just basically indicates when a number has got larger than will fit in 4 bits. So the parity overflow holds the result of parity or overflow. It depends on the instruction used. Not going to go into a lot of detail about that one. Maybe we might encounter it. I was listing it here for completeness. Now the next one is N, or add, subtract. It basically tells you what the last instruction did, whether it was an addition or a subtraction, and as you can see there are bits. So it was 0 if it was add, and 1 if it was subtract. Very useful when you're doing some complicated maths using assembly code, which hopefully we won't need to do in this series. And probably the next one that you use the most after, so the main one you'll use is the 0 flag, or not 0 if you want to test for not, but there is the carry flag, and this determines if you say you're doing a bit of maths and you add two numbers together and they're larger than 255. They're not going to fit inside a single byte of memory. So you know to do something after that happens, the carry flag is set on those occasions. It also works for negative numbers as well when you're subtracting. So that's a lot of flags. Now, all of these flags are stored in a special register. We actually mentioned that in the last episode. So it's part of the 16-bit pair AF, accumulator and flags, but you cannot access the F register directly. So the flags are set when you execute any of the commands that affect the A register, or when the HL register, which is the register used for doing 16-bit maths, are used in a similar way. And once again, if you've got the Rodney Zach's book, it has more details in there for you. Now, as an example, if we want to check a value against what's stored in the A register, we would use the CP command, which, as an example here, we're comparing what's in the accumulator with the value 80. So this would then set several flags depending on the current value in the A register. So if the value in the A register, as an example, was 40, then subtracting 80 away from 40 would set the carry flag, because we went negative. In other words, we're overflow, and it was also overflow as well. Now, if the value of the A register was 80, it would set the 0 flag, so you'd get a match. So you can sort of start to get an inkling of what these are going to be used for. So let's reiterate what I just said. Now, the important thing here is what is in the A register is not harmed, because you think, well, what's the point of the CP instruction if I could just go and subtract? But in this way, it doesn't damage what's in the A register, it throws the result away. All you're interested in is setting the flags based on what you've specified, so that makes it much more useful. So you use the CP instruction a lot. Okay, and what do you use them for? Jumps. So a jump in Z80 changes the program counter. Now the program counter is a special register which indicates which instruction is going to be executed next. So by changing the program register, you can jump around your program. The jump can be a straight go to a specific spot in memory, or it can include, but it can also include a condition based on your flags. There are two types of jumps: jump direct and jump relative, indicated by JP and JR. So JP being short for jump and JR being jump relative. They're both very similar, especially when you're looking at your code, but it is better to use the jump relative one because it uses one less byte of memory and it also executes faster. And the best strategy when you're writing a program is use jump relative in the first instance and only change it to jump direct, or reorganize your code a bit when the assembler complains. And the assembler will tell you when a jump relative is too far, because you can only go plus 128 bytes and minus 127 bytes back the other way. Now, adding a condition is really simple. All you do is you put the JR or JP command and then add the name of the condition, so Z for 0, NZ for non-zero, C for carry, NC for carry, and you use the other letters accordingly. They're the main ones that you do use. So jump relative, if not 0, you would use JR, NZ, comma, and then the name of a label indicating where you want to go. So rather than specifically say the memory address where you need to go and have to even think about memory addresses, assembler allows you to put labels on things. So all you really have to do is put labels and let the assembler look after where in memory that is. It makes things much easier. Otherwise, programming directly in machine code is not a good idea. Oops, I went backwards there. Right. So, to make things a little clearer, let's try an example. Say we wanted to do a particular task 10 times. We could do it as follows. So, hopefully this is clear enough. So the first thing we do is load our B register, which is quite often used for loops and counters. So we load it with the value 10. So remember the LD instruction from the last episode, whatever is on the right gets stored in the thing on the left. The next part is, I'm actually point with my cursor here, the next part is a label. You can see it's a label because it ends in a colon here. And normally when we write our assembler code, we tab in the instructions and have the loop variables just one in, just so that you can see them easier. But you could have it level with this as well. And notice I've put plenty of comments in here. And then our next instruction, we did cover this in the last episode, is decrement whatever is in B. So B was 10, so this will make the first time through we hit here B 9. And then we hit our jump instruction, so jump relative when non-zero to the label loop. So when we hit here the first time, when we decrement, so decrement affects the 0 flag and also the carry flag. So the very first time through here, the 0 flag won't be set, and we'll loop round to here. And then we'll hit the deck B again, and then we'll be 8, and we'll hit here, and we're still not 0, and we'll keep on going until the final time when B is 1 here, it'll get decremented, made 0, and the 0 flag will be set, and then we won't meet this condition. So we will be 0, and we'll pass on to the next section of code. So as you can see, it's not that complicated, and it's only 1, 2, 3 instructions. A label doesn't count as an instruction, all that is a marker to say where a memory location is. So we've done our very first loop. Now, if the code in here, I mean obviously you may have more code in here. At the moment this is like a single byte instruction, and this is only a 3-byte instruction. So we really don't have a lot of code inside here. But if there was a lot more code inside this loop, if it was larger than 127 bytes when it's compiled in machine code, the assembler would complain. Okay, and then we only need to change it to a JP instead. Exactly the same syntax, just change the JR to a JP. Okay, now loops, another way. Now the Z80 is what's called a KISC chip, complex instruction set, rather than 60502, which is more RISC or reduced instruction set. So there are actually several ways of doing the same thing, which is good for readability, but it does mean that the Z80 doesn't execute instructions as fast as a 6502. But to make up for that, most of the time the Z80s are clocked much higher. So there is actually a better way of doing this particular loop. So, and you will find quite often there are several ways of doing the same thing. For what we're doing in this thing, it doesn't really matter which one you choose to use. I'll probably use this particular instruction I'm about to demonstrate a fair bit in my code though, because it's quite useful. But the most important thing when you're writing code, any sort of code, whether it's in assembly language or in other languages, is to make sure that you can understand what the code does the next time you come back and read it, or when somebody else needs to have a look at it. Performance and memory we use don't really matter in the particular game we're looking at. I find it's better to write something, get it working, because that's actually one of the harder things to happen, and then only look at optimizing things when you need to. Readability at this stage is more important than performance. So let's get on with our instructions, example. So, for the curious, the Z80 has a rather helpful instruction called DJNZ, a bit of a mouthful, which stands for decrement and jump when non-zero. So you can see this is going to help us out a little bit here, or hinting towards. It only works on the B register, and the jump is relative, so it's only for small jumps. And our example goes as follows. So I'll just pop it all out. Right, so like before, we set B to the number of times we want to go around the loop. We set our loop label But this time there's nothing inside the loop. I mean, we could put more code, of course it does other things, but this time DJNZ will decrement B and then jump if B is non-zero round to loop. So it only works on the register V, and then we can put whatever code we want here. And once again, it's simplified it, so it's made it easier to read. And as a bonus, it's faster. So it only takes 2 bytes, and obviously you don't have the execution of the decrement instruction as well. It's all built into this one thing. So it's a little faster too. So if you have lots of little loops, just this one little change can actually give you a performance boost. Okay, now, oh sorry, my graphics have popped up a little bit, spoilt what we're going to go through. So we're almost done doing the basics of Z80 programming. Now we need to just cover off a couple of concepts. So it's probably a good idea to understand bits, bytes and pixels. And nibbles. So our games uses pixels, which are represented by one or more bits stored in our subsystem's memory. And a single location, as the graphic that popped up early, can be thought to represent this. And notice the numbering is from the right to the left. So the value 1 is if this box here was checked. The value 2 is if this box was checked and this one wasn't. The value 3 is if both of those. So you just, that's binary mass, and gradually work your way across to the left hand side. And it's important to understand this ordering from the left to right. Right. So these 7 bits allow each byte to contain a number from 0 to 255. Not very big, but quite useful in 8-bit programming, and you can combine them together by by having more than one byte. But that's a topic for another time. We'll cover that when we use it in our game code. So now one more thing, and this is I've mentioned this already, is that the 2 halves of a byte, bits 0 to 3, this part here, and 4 to 7, as you can see, you put a dividing line down there, are called nibbles. So that's the lower nibble and that's the upper nibble. And each nibble represents a number from 0 to 15, or 0 to F in hexadecimal. And what is hexadecimal, you say? So us humans have 10 fingers and 10 toes, so thus our counting system is based on 10 groups of 10. But computers, all they really know underneath are zeros and ones, whether something is on or off. So not surprisingly, numbers in computers are much better represented as numbers that are made up of the power of 2. Hexadecimal is a way of easily expressing numbers from 0 to 15 with one character. And here's the table, which, sorry, it had already popped up. And it shows, 0 to 7 is exactly the same in hexadecimal, but once you reach 10, we start using the first 6 letters of our alphabet. So we go to A to F. And combining them together, so each letter represents a nibble, so easily splits your 8-bit number up into 2 halves, and then you only need 2 characters to express up to 255, and as you can see, it already saves a character, and it also easily splits up the 2 halves of the byte as well. So it's actually a really useful way of expressing things. But you will find when you're going through, if you're not used to hexadecimal, that it's great to have the Windows calculator up in programmer mode, so you can easily convert between the two, or perhaps you have a physical calculator that does the same thing. Just about every calculator does. Okay, now that's the end of this particular episode, and hopefully it's it was enough for you to be able to absorb the basics of Z80. Which I really thought we needed to cover before we could get on and drill down into our game. But next episode is definitely getting into our game and making it do something. So we'll get back to the game loop, which we've covered before, but we'll put some code together to make our spaceship move back and forth, and maybe our bullets shoot up to the top of the screen. So at the end of the next episode, you'll have something to play with. Alright, I hope you are enjoying this series. I can't promise when the next episode will be, but I'll work on it over the next few weeks and we'll see how we go. Thanks to all my subscribers. Thanks for watching, and I'll catch you next time.